Welcome back, everybody. In D.8 video part B, where you're at right now, we are looking at an example problem of a system. So depending on if you have Mr. Thrasher as a teacher, you may have already practiced these. Maybe you're watching this video ahead of time. Maybe you're watching it after some attempts just to get some helpful hints for how to solve these. I do recommend, this video has a single problem. I recommend when we start it, you hit pause and try it first. See how far you get. Then watch the video. Remember, chopping onions is the way to go. That's probably a better approach than simply just sitting back and watching the video and potentially getting distracted by things. But here we go. We're going to remember our set of rules or our strategies for solving these systems of problems. What were they? Remember to identify the different objects in your system. That doesn't mean write an essay. Just make sure you're aware. Is there one object or two or three? I like to be super organized, so I will then set up my free body diagram for one object and then for a different object. Make sure we draw our coordinate systems. Here's actually a helpful hint, and I'll explain this as we go in the actual problem. When you see an object and you're like, I think that object in the problem is moving to the right, or maybe it just says in the question, this object is moving to the right, make that the positive direction. If you remember, we could always choose whatever direction we wanted in the past, and while that's still true, if you don't follow this idea, it is very likely that you're going to end up with a problem, a setup that's incompatible with your two different objects. I'll explain more later. But for both objects, think, which way is it going to be moving? I'm going to make that the positive way, the positive direction. We'll draw free body diagrams, we'll break anything into components if we have to, and then we'll apply the second law. Also, let's remember that any forces between the two objects, those must be equal to each other by Newton's third law, and also their accelerations have to be equal to each other because they're connected. They're part of the same system. Okay, that will often help us solve these questions. Here we go. Here is the problem. It says I have these two objects, a mass of 3 kilograms and another mass that's hanging down of 5 kilograms. They're attached by a string. That string we'll assume has no mass. We'll assume this table has no friction. And there's this pulley. We'll assume there's no friction in this pulley. Okay, this pulley is just a way to redirect this string so I can attach this hanging mass. It's asking us to use Newton's second law to calculate the acceleration of these objects. Remember, they're going to be the same thing. And also to calculate the tension in the string. So here's where I recommend you actually hit pause and you try this on your own first, okay? Did you try it on your own? I highly recommend that. Here is our setup. What is the first item on the agenda? Let's make sure we recognize that there are two objects. There's these two masses. Okay, I'm going to make sure I'm nice and organized for these two different objects. Let's set up the coordinate system, and then let's set up the free body diagram for each. So for this orange one, I know you might not be able to color coordinate, but at least maybe label this. Here I'm going to do it for the 3 kilogram object. Now, based on this scenario, it looks like this heavier block, this more massive block, is going to be tugging on this string and dragging this block to the right. I might be wrong, but it seems like this block is going to move to the right. So I'm going to say right is positive, and because I'm usually doing this, I'll say upwards is positive. What's my free body diagram for my orange block? I'm kind of ignoring this for right now. I'm not worrying about this object. I'm drawing the free body diagram for this block. Of course, there's some normal force. I'm going to call this normal force. I'm going to use the subscript 3, okay, the normal force on this 3 kilogram object. There's a weight. I'm going to call that the weight of 3. Any other forces? Yeah, there's this tension force. This string is tugging on this object. Now, yeah, it's happening because of this hanging block, but don't overthink it. I see a string. It looks like it's tugging it to the right, so let's just say there's some tension force to the right. Okay, bam. Now, let's go ahead and try this for the 5 kilogram object. I'm nice and organized. That's the key. Now, which way do I think this 5 kilogram object is going to move? Well, it's a little more massive than this other object. There's no friction or anything. Nobody is pushing it to the left or anything. I think this block is going to slide downwards, is going to move downwards and drag the orange box with it. So I'm actually going to say, this is maybe a little different, I'm going to say that downwards is positive. That's usually not how I define direction if you've watched my other videos, but I think that's the way this object is going to move. And there was that helpful hint that says, well, put that as positive. I'll explain why that works out well later on. Let's set up the sum of the forces. There's no horizontal forces, so I'm just going to look at the vertical forces for my 5 kilogram block. Oh my gosh, excuse me. I shouldn't be drawing the sum of the forces. I got to finish my free body diagram. So there's no forces acting horizontally, so there's just this upwards tension force, right? There's this string that's tugging on it. And there's, of course, the weight of that green triangle. I'm going to call that W5 because it's 5 kilograms. Okay, nice. Now, maybe before we write up the sum of the forces, notice these two tensions. This green block is tugging on the orange is tugging on the green. That's those tension forces. Those are the third law pairs. Those tensions are going to be equivalent to one another, okay? But let's try setting up the sum of the forces for the 3 kilogram block. So sum of the forces for the x direction. I'm still underneath this section. Maybe I'm nice and organized like this. Here I go. What is it? There's just one force. There's T. That's equal to the mass of the 3 kilogram object times the acceleration. There's no friction. There's no forces to the left. I could do the sum of the forces in the y direction. It's not really going to help me out a whole heck of a lot. I have normal force minus W3 equals MAY, but it's not accelerating up or down, right? So it's just going to be N minus W3 equals 0. If it asks for the normal force, that's a little proof there, but that's not super helpful. Let's write out the sum of the forces for this block here, okay? Now let's do it in the y direction because there's no horizontal forces. I'm actually going to move my floating head up. Oh, there I go. Ooh, okay, I can look down on you. Let's set up the sum of the forces now down here. Sum of the forces in the y direction. Now remember, I'm saying down is positive. So I'm going to make W5, the weight vector, positive minus the tension. That equals the mass of the 5 kilograms times A. Now, why was it important that I had downwards as positive? Remember, they have the same acceleration. This object, it certainly looks like it's going to accelerate to the right. This object looks like it's going to accelerate downwards. If I use, I'm kind of going to put it in parentheses. If I did my usual upwards as positive, I'm going to delete this in a second. I'd have T minus W equals M5 times A. This would actually not ultimately be right. Because is this green triangle going to accelerate? Look, it's positive. Is this green triangle going to accelerate positively upwards? I don't think so. I think it's going to go down. So that's why this version here is more accurate, because the acceleration is a positive on this right-hand side, and I think it's going to accelerate in the positive. If I had this, then technically this acceleration would be the negative of this acceleration, and I might end up with ultimately an algebra mistake. So that's why it's worthwhile to think about what direction you think the objects are going in so that you could plug in these accelerations into each other if that's helpful. Don't worry, you'll get practice with that. Okay, so there's my setup. On my next slide, I'm going to get rid of some of these free body diagrams. I'm just going to have these equations so I have a little space to work through the algebra. But if you need to hit pause, make sure you understand how I've written these. They should hopefully make sense to you. Ooh, okay, I'm back. I reset. I'm now back down here. I got rid of the free body diagrams and stuff. You could always go back in the video if you need to see them again. I also didn't copy over the y direction for this orange box. It's not going to be super helpful. Now we have these two equations. Let's solve for the acceleration, okay? And that I can do using this equation, recognizing that these two tensions are the same by Newton's third law. The green triangle is pulling on the orange box. The orange box is pulling on the green triangle. That should be horizontal. Those are the same. So I can actually take this tension and I can plug it in right here. So what do I have? W5, the weight of the 5 kilogram block, minus, I'll switch to orange, M3 times A is equal to M5 times A. Well, let's do this. W5 is equal, if I add this term to both sides, M5A plus M3 times A, I can actually factor out an acceleration. W5 equals the acceleration times M5 plus M3. This was just an algebra step. Since there's an A in both of these terms, I could factor it out. So how do I solve for A? I'll divide both sides by M5 plus M3. Do it right here. M5 plus M3. So I'm left with the acceleration is equal to W5 divided by m5 plus m3. W5, that's just, sorry, I shifted things and I'm going to kind of work this way horizontally. W5, that's the weight. So that's simply the mass of the 5 kilogram object times g divided by m5 plus m3. That's equal to m5, well, that's 5 times 9.8 divided by m5, well, that's 5, plus 3. So in my calculator, I should do 5 multiplied by 9.8 divided by 5 plus 3. And the acceleration I am doing, check in the comments, let me know if I got the wrong answer, but I got 6.125 meters per second squared. Maybe you round it to 6.13, right? Round to one or two places. That's the acceleration. Fantastic. How could I figure out the tension? Well, I'm going to change colors. I'm going to go to purple, but I could actually use this equation. Let me give myself a little bit of space. I know that T equals m3 times A, and I just solve for A. So the tension, what's the 3 kilogram mass? That's 3 kilograms, of course, times 6.125. What's 3 times 6.125? Again, I'm going to check the calculator that I have. I got about 18.375 newtons. Again, if you round it slightly different, that's of course okay. So knowing that those tensions were equal would allow me to plug one equation into the other to calculate what it was asking. And then it was pretty easy to go back and find the tension force once I knew that acceleration. So that's what these problems are. You're doing the same stuff as before, but you're doing it now maybe once for each object, and then based on what you know about Newton's third law and how the objects are moving together, you can kind of substitute in some of these things, okay? Now, there'll be another way to kind of approach this talked about in the next video, all right? But make sure you understand this way. This is kind of the go-to method, the fail-safe method of solving these problems. But that's it. That's the video. Thanks for watching.